In the last video, you learned what a matrix is, a description of how the coordinate grid changes after a linear transformation, by keeping track of where the basis vectors I hat and j hat land. But is there a way to represent multiple transformations as a single matrix? For instance, let's say that we stretched the coordinate grid and then rotated it, or we sheared the grid and then stretched it. In this video, we go through matrix multiplication. In schools, you're normally taught matrix multiplication after matrix addition. This is because algebraically it's much simpler. However, learning matrix multiplication before addition will help you intuitively understand the underlying geometry of what's happening much more clearly. Let's start with two basic transformations. First, we stretch space horizontally by a factor of 2. Then we rotate space by 90 degrees counterclockwise. When we perform these one after another, the final composition of these two transformations is a distinct linear transformation, which can be represented with a matrix of its own. Let's give these matrices names. We'll call the matrix that represents the stretch A. We'll call the matrix that represents the rotation B. Finally, we'll call the matrix that represents the combined transformation C. C is what we're trying to work out. Since a matrix is just the representation of where the basis vectors land after a transformation, if we know where I hat and j hat land after the two successive transformations, we'll know what matrix C is. Let's start with tracking I hat. First, we apply transformation A. Stretching the grid sends I hat from 1, 0 to 2, 0. Then we rotate the grid by 90 degrees, sending 2, 0 to 0, 2. The first column of matrix C is therefore 0, 2. Now we do the same thing with j hat. First, we apply transformation A. The vector 0, 1 is unchanged because the stretch only affects the horizontal direction, so it remains 0, 1. Then we apply transformation B. Rotating by 90 degrees sends 0, 1 to negative 1, 0. Therefore, the next column of matrix C is negative 1, 0. This gives us the new transformation described by matrix C. Here, C captures the effect of applying a stretch and then a rotation as one action, rather than two separate ones. This process so far is kind of long, and it requires a lot of visualization. We need a method that lets us compute the final transformation directly, without having to draw everything out each time. This is exactly what matrix multiplication is, and in this next part we're going to derive the entire process from scratch. Let's start off with a general case. We want to work out where transformation A sends a given vector x, y. We know that the first column of A tells us where I hat, which is the basis vector in the x direction, goes, which creates essentially a new basis vector. In a similar way to how I hat is scaled by how many steps we take in the x direction, our new basis vector is also scaled by x. We know that the second column of A tells us where j hat, the basis vector in the y direction, goes. This new basis vector is scaled by y. This gives us the following. A applied to the vector xy equals x times the first column plus y times the second column. This in itself is a new vector, which tells us where each x and y coordinate goes following transformation A. Now we can apply transformation B. The first column of B tells us where the new basis vector, the one which replaces I hat, goes. The second column of B tells us where the basis vector which replaces j hat goes. Working through this and grouping the x and y terms together, we end up with this. You'll notice that this is identical to matrix C applied to the vector xy. This is exactly what we want, since C is just the combined transformation of A followed by B. So now, just a quick recap before we move on to a worked example. First, we applied A to the basis vectors, which I'm writing in shorthand as E. So that gives us A times E. Then we applied the transformation B to the new basis vectors, B times A times E. This gives us the transformation C equals B times A times E. Here the order does matter. Matrices just represent linear transformations, which are just functions. Given this, it might seem like the right-hand side is written in the wrong order. But just like with functions, we start with what happens inside the brackets, and then we work outwards. Now let's look at a worked example where this time we just focus on the core calculation. Let's multiply these two matrices. We want C equals B times A. Each entry of C is a row of B combined with a column of A. The top left entry is row 1 of B multiplied by column 1 of A. The top right entry is row 1 of B multiplied by column 2 of A. The bottom left entry is row 2 of B multiplied by column 1 of A. And the bottom right entry is row 2 of B multiplied by column 2 of A. This gives us the final resultant matrix, C. I hope you enjoyed this video, and hopefully by this point you're comfortable with what's actually happening under the hood when you multiply matrices. Also, if you're interested, I offer maths tutoring. Email axiomaticlearning@gmail.com for inquiries.